9.6. It's going to be all about functions in two variables. Functions of three variables, where the idea here is z is a function of x and y. Okay, most of them will write it kind of like this. We're going to be talking, and we'll be talking about how the changes in y and x, or changes in y and x affect z. We'll talk about what are the shapes of these graphs looking like. We'll talk about domains and ranges. So specifically, I guess I want to talk about this first. Domain, in years past has always been about the x's, but now it's going to be about the x's and the y's. And so instead of being x, say, goes between, let's just say that x in the past would be x went between 1 and 3. Maybe that was your domain, hypothetically. Well, now it's going to be something more like this. Maybe x goes from 1 to 3. Well, 1 to 3. At the same time, y goes from, say, 0 up to 6. So in essence, we might have a box that looks something like this, where this whole region is my domain, 0 and, say, 6. Okay. Other times, it could be all reals. For instance, in the case of this guy, x and y are, x is all reals. And I know that because if you look at it, this function is basically a quadratic in terms of x. And here, this is a constant in terms of x. And if you look at y, y is also all reals, because y, really, this function, z is a function of y, it's just a linear function. And there's nothing I can't put in there. Okay, the things that are going to cause us issues are going to be the same things that have always caused us issues. 1 over 1 minus x minus y. Something like this. If this was your f of x and y, or your z equals, if you will, we know that 1 minus x minus y had better not equal 0. Okay? As a matter of fact, it better be greater than 0. Okay? First, I should have said, I wrote equals. I should have said this to start with. But more importantly, it better be positive in there, right? So what does that say? It says that 1 better be greater than x plus y. Well, wait a minute. X plus y is an equation, and you can rewrite this as 1 minus x is less than y. And that equation looks like this. It's got a slope of, it's got an intercept of 1 and a slope of negative 1. So it looks like this. It's kind of a dashed line, kind of like that. And the parts that we want are the y's that are less than the values that are less than this line. So down here. You could try that with a test point. For instance, 0, 0 comes to mind. You put 0, 0 into here, 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 any of those, you will see that 1 minus 0 is 1, and that's hunky-dory. And so any value down here in this region will work, versus up here you get 5 and 7 or something. 1 minus 5 minus 7 is a negative number. That doesn't work. So the domain is this region down in here. Another one that comes to mind of those is this fella. And so domain here, again, the idea is 1 minus x squared minus y squared better be bigger than or equal to 0. It can be equal to 0 because it's not in the denominator this time. So in other words, x squared plus y squared, if you move them over to the other side, are less than or equal to 1, it looks like. This is a circular region with a radius of 1. So this would be your domain. So 0, 0 works again, for instance. A half would work. But out here somewhere, no go. Okay, so domain has always been important. It will always continue to be important. Again, thou shalt not square root negative numbers. Thou shalt not divide by 0. Those are the biggies. You can't take the ln of 0 or a negative number, so whatever, something like this. If this was my z value, we know that 2x minus y squared better be bigger than 0. So y squared had better be something like this. And you can do this a couple of different ways. It's up to you. I don't really care. Maybe I write it like this is equal to a half of a y squared. If you're good, you realize that a half of a y squared looks something like this. Okay, oops. And the x's that I want are greater than this, so it's this stuff in here. If you're not sure where to shade it, oops, this should be a dash, and that should be a dashed parabola. Dashed parabola, like so. Okay. If you're not sure, again, you just pick a value. Well, here's a perfectly good value, 2, 0, yeah? If you put 2 in here and 0 in here, you get 2 minus 0 is 4. The ln of 4 is perfectly fine. Versus up here, this is the point, like say 2, 5. That'd be 4 minus 25. That obviously wouldn't work. So it's the values inside of this parabola. Okay, now, other people might at this point go, you know what, I don't like to do it that way, so I want to do this. So the y's are less than 2x. Be careful, because technically speaking, they are like this too, right? And so here's the square root of negative 2x. Here's positive 2x. That, by the way, that just looks stupid. I can't leave it like that. So watch me flip them around, because the little one should go on the left. And that would be our domain. And so again, it's this region in the middle. There's no difference whether you do it in terms of x equals y squared or the other way around. The region doesn't change. Okay. Domain. Again, I'm not gonna harp too much on the range. Rather, the domain's a big deal, and I think that's pretty important for us to keep an eye on. Now, when we do these things, what I want you to think about is this: is that yeah, we could do all kinds of cool different graphs, and we'll look at some of them. But what I really want you to think about is this: is that z, you could think of it as something like your blood pressure. And x could be something like your stress level, and y could be something like the amount of sleep you've had recently. And so, it could go something like this. Maybe you have a nominal blood pressure of 100, something like that. Go a little higher than that, maybe 130. And suppose you add 2 for every x you have, and you subtract 3 for every extra hour of sleep you get or something. This would just be a nice easy function like this where you boiled it down, and maybe this comes out that that's what it actually is. And it just says this: as stress goes up, so does blood pressure, right? By the way, by 2 points. Okay? And then as sleep goes up, blood pressure comes down 3 points per hour, or whatever it happens to be. Okay? Whatever you happen to have measured your sleep in. This one is nice and linear. That's not always true. For instance, it could be a situation where you have 130, and then there could be some kind of a quadratic coefficient on there, but probably not x squared. That would be a little ridiculous. If it was going to be quadratic in this situation, probably some small quadratic. You can't really have the person's stress level just like blowing the top off their blood pressure. Even on a day when you have a lot of stress, maybe you feel your blood pressure going up, it's not a quadratic. It's not a hardcore quadratic like 5x squared, because you literally would blow out and have a problem there. So we'll see problems like this. Again, this guy here is linear, and so it's just a nice, plane, the equation of a plane. We'll be talking about that coming up fairly soon. The equations of planes, or actually we do that in 9.5 rather. And we're going to continue with planes, and again, it's just a two-dimensional, or a three-dimensional line, rather. Just a line that's been extended out in another direction off to the sides of it. This guy here has that idea of a quadratic shape to it. So when you look at z, in terms of x squared, what you're going to see is the general gist of this equation is going to be here's z and here's x. And so viewing it from this point of view, you would expect to see some sort of a parabola shape to it. Okay? Viewed from the y side, you would expect to see basically this would be constant, constant. These are all constants. So you let y be negative, and it would come down something like this. So in other words, z and y is more of a linear relationship versus z versus x as a quadratic relationship. All right. So this idea right here is kind of a big deal because that is one of the things you're going to be asked to do. Is actually talk about making a trace or sketching a trace of what the function looks like. Okay, so here is a function that kind of comes to mind right off the top of my head. And I'm going to do cosine x minus 2 e to the minus x minus y. And then, plus 2. Now, when I first look at this problem, I think to myself, okay, well, interesting, I guess. So let's let y be a constant. Now, what constant? Doesn't really matter because that won't change the shape of the graph. It'll change where it is on the graph a little bit, but it won't change what the actual thing looks like. Now, what I like to do is I like to use a program called Desmos for graphing. Now, we're not going to graph this in 3 dimensions right now. What I want to graph is in 2-dimensional only. Now, what I'm going to do is I'm going to come in here and I'm just going to kind of see what this looks like. I'm going to actually, you have to do y equals in this case. And I'll explain that a little bit why. Because this function only graphs in terms of y and x. So what I'm going to do is I'm going to let my z be y. And right now I've got this thing. The 3 cosine minus 2x minus 2 e to the parentheses negative x minus, now I'm just going to call this a variable like b here, okay? And I'm going to let that b change in a minute, and you'll see what I mean by that. And then I'm going to arrow down out of that. I'm going to say plus, what was the rest of the problem? Plus 2x. Okay, so there's my function. Now, as I change this b value, you see, this is just what the shape of, that's how it's affecting this thing as I go back and forth between negative 10 and positive 10. But viewed from the side, what I'm going to see is this function I get here in a few minutes, and I will graph it in 3 dimensions in a few minutes. What I'm going to see is the shape of this goofy thing changes a little bit as I affect y. But from the side, I'm going to see that z, if I treat this as z and this is x down here, that I'm going to have the same basic general shape no matter what happens to y. It's tweaking this in a little bit, but not too much. Okay? So this is how I would sketch that out on my paper. The trace in the z and x direction would look something along the lines of this. Now, why do I care? Well, I kind of like to have an idea of, or something like that, whatever it was. I would kind of like to have an idea of how is x affecting my z values. Okay, what kind of a relationship is it? That's the idea here. Now, back in the old days, which were not good days, back in the old days, a guy had to actually try to sketch in 3 dimensions from these 2D shapes, which, let's face it, was a giant pain in the butt. Now, watch me come in here, and I'm going to tweak these. I'm going to play musical chairs with these guys. I'm going to leave this. I'm going to change it up just a hair, and I'm going to make this also times b. Okay. Now, what I'm going to see is this time is that I'm going to let this be a constant. Okay, this is now z is equal to, and now this is my y value in here. And so my x's are just constants, and I can change what those constants are, but you see it doesn't really change what the shape of the graph is. Okay, and so it's going to have that same general shape every time. The only thing that's going to happen is well, how does it get shifted a little bit? And so as you see, we had several versions of this guy over here. Most of this up here didn't change for this guy, but we had some that looked like this, and some that went like that, and some that went like this. For this guy, we have him up here, and so forth and whatnot. Okay? That's what they look like in this direction. Nice. Now, the other thing I like about this Desmos program is you play your cards right. You can also do, you can put a B equals. If I do it, okay, I'm going to pause for a second. Alright, and then we'll also take a look at, well, what happens if you hold Z constant? Okay, now that's a little trickier in this problem. So I'm going to do that again in a couple of minutes with an easier problem. But we can also hold Z constant. Okay, if this stayed 8, for instance, then we'd have to be able to graph this thing implicitly, which is kind of hard to do. So if you try to solve for y, yeah, it's doable. It's just kind of a mess. So I'll only give you an easy problem of that kind. So for instance, this guy here. Alright, so if you look at it from the zx side, the traces will look something like this. I see quadratic, I see a linear term, I see another linear term, and I see a constant. This is a constant as well. So I expect it to look something like, give or take, something like this. Now it's going to slide back and forth, side to side, and up and down, depending on what y is. So again, back into here. I wish I had paid attention to what the equation was. 3x squared plus y squared minus 2x y. Okay, I'm going to change that in just a minute. And then plus 1. Okay, so clearly it can't graph that because it doesn't know what to do with that. So what I'm going to do is I'm going to come over here and I'm going to say y equals. Now see, it graphed that one. That's bizarre. Okay, so we'll come back to that in a minute. So it graphed it. It did graph it in terms of implicit that time. I don't know why it wouldn't do that before. But, alright, what I'm going to do is I'm going to come in here and I'm going to make these y's a's. Okay, and I'm just going to let them be different constants. So what I'm going to see is, look at that, it's a parabola, just kind of like I thought it should be, right? And so viewed from z versus x, I'm going to get a parabola. It's shape-shifting slightly, side to side, and up and down. But from this side, it's going to be this general shape as a parabola. Now, from the z versus y side, z versus y side, I see quadratic, I see a linear term, and everything else is constant. But again, it's going to be a little bit fatter of a parabola. But again, it's going to go up and down and side to side. And so all I have to do now is come back to Desmos, and I'm going to trade that with an A. I'm going to make this go back to y, or not y, but I'm going to make it be x. That's my new y value. Oh! What are you doing? And obviously this was 5xy a second ago. Now I'm just flip-flopping it. And again, look at that. It's a parabola again, kind of like we thought it should be. Okay, now, how is that helping us in terms of actual graphing? Again, it tells us more about what to expect when I graph a function. It tells me about how they interact with one another. Tells me what kind of relationship. Later on we do derivatives. Derivatives talk about the rate of change. This is going to help me with that to see if my answer seems reasonable. Okay, so in the 3D calc plotter, you are going to go in and you are going to go to graph, and you're going to go to clear all graphs. That's the first thing you want to do. And then I like to do it doesn't matter which function you do it in. So you get 3x squared plus y squared, and what's the rest of this dumb thing? Minus 2x oops, 2x plus 5x times y plus 1. And when I hit graph, I get this goofy looking thing. Now, viewed from the side, viewed from the side where I'm looking at it from the, right now currently this is the y-axis here, so this is, I'm looking at it basically from the, oh no, what just happened? Oh, stupid laptop. Stop it. Oh, go back. Shh. I think it's more my stupid finger got in the stupid way. Alright, we'll try that again. 3x squared plus y squared minus 2x plus 5x times y plus 1. Okay, now again, if you spin it a little bit, okay, looking at it, viewing it from the side here, this is the z versus y side. I got that whole parabola look going on. Notice that it does spin it slightly sideways in that we have the x times y, which puts it kind of, it grows up and down the x and y plane. However, down the line y equals x. Again, if you spin it this way, you can see cutting across there is that parabolic look to it. And that's all we're saying. So when we look at these guys, z versus x and z versus y, what I see is very much of a parabola when viewed from the side. It's that idea of chopping it flat and then looking at the side view of the thing. Okay? Well, that's interesting. Now let's go out a little ways here and change our window and see what it looks like if I go further out. Hey, look at that. Son of a gun. What do you know? Same basic procedure. Oh, what did you do? What? Ah! Oh, I'm angry. What is going on? My computer hates me. It probably knows what I call her. It's payback time. Voila. Okay, so we're good. Now, what I'm going to do now is go back into here and I'm going to ask you a question. What happens if I let z equal 0? Well, that's interesting. Well, if I let, not 0, but if I let it equal something, some constant value, what I'll end up with is this idea of 3x squared plus y squared. Now remember, these coefficient pieces here and here, okay, they don't do a lot for me, but you might remember back in the day, you ran into a few of these guys. I'll write it this way because it's easier to go with right now. Plus 1 equals some constant. Well, viewed from above, what you're going to see is that's going to be the idea of an ellipse. Okay? And as I let this thing change, it's going to make this ellipse change. Maybe make it a little bit fatter, scoot it up and down, right and left. But that's kind of a cool thing, because if you come over here, back to the 3D calc plotter, and roll this around and look down the business end of the thing from above, if you go out far enough, which we haven't gone out far enough, I don't think yet, if I go out far enough, the thing should be coming back up. So I'm going to go out a little bit further here and see what happens. not coming back up yet. Alrighty then. Yeah, well, eventually it should come back up. So unless I type my function in wrong, if it looks right. I'm going to pause you for a second. Alrighty then. Sorry about that. I was thinking improperly a minute ago. This has the idea of this 3x squared plus y squared, and I was thinking in my head, oh, that's got to be, it has to be an ellipse, but I was wrong. I was thinking of the wrong kind of, it looks like it should be, but what I was thinking of was the wrong, what I ended up with, it should be like a hyperbola when viewed from above. And so what I did was I went into Desmos. You'll notice that it likes to have a y on one side of this thing in order to graph implicitly. If you tried to bring this crap to the other side, the 5xy over to here, it didn't like it. And I'm not really sure why. Oh, part of it's over here, but anyway, that's what it looks like. So all I did was I just subtracted the 5xy to the other side. Probably would work the same way if you put a y squared over here. It just doesn't know what to do if you don't do it. A is my z value. Matter of fact, you could even have called it z, but I was too lazy to do that. So what I did was, viewed from above, we have this look going on. So this is looking down on the x and y plane. So viewed from the x and y planes, you see how we have this going above up here? If I let my y's change, if my y's went down towards negative, or down toward 1, now down to 0, and now out to 2, that's what I'd be seeing. In fact, right here on the x-axis, right here at 0, this is what happens when you are on the xy plane. And so if I come back, if I come back into my 3D Calc plotter, I change my stupid windows back to, let's go negative 5, 5, negative 5, 5, 5, negative 5, 5. Okay. What I end up with is this goofy, what happened here? Negative 5, 5, negative 5. Okay, I guess nothing happened there. Oh, there it is. I was just sitting on its side. If you spin it over and look at it, looking down up from above, and one way to do that is to come into here, and you can view the XY plane from above. So that's looking down onto the XY plane. And looking down to there, it's kind of hard to tell what's going on exactly right now. But if you roll it around a little bit, you can see that if you look down on it from above, okay, it very much is going to have the same general look as this thing right here. Okay, that is, it comes in and then it goes back out. Well, the reason we study this guy so much, that is the idea of letting z be a constant, that's what is often referred to as a contour plot. So if you let z equal a constant, you get what's called a contour plot. Now we're actually going to spend quite a bit of time with this later on. And so this is just a special case. So if you let z equal, you're like, well, contour plots, isn't that for like up in the mountains? Well, sure. So you could let z equal your elevations, maybe 100 feet and then 200 feet and so on and so on. What you'll find is it might look like this. That might be the 100-foot markings. Okay, and then you let it equal 200 feet, and now it's in here like this, and these would be the 200-foot markers. Okay, and then over here might be the 50 markers. Okay, it's the same idea. That's a weird-looking graph, Jay. Had a bed. Every now and again I draw something, and after I draw it, I'm kind of like, that's not too cool, but oh well, I've already drawn it, so there it is. Did not mean for that to happen, so whatever. There's our contour plots. So, again, to sketch when you let z equal 0 is what is called a contour plot. Now, why do we do that? Why do we just assume that c is a constant, or y is a constant, rather? Well, it's the same idea as back when you were a kid and you did a science fair project. Okay, and so you're going to grow lima beans, okay, and you're going to put them in like little cups, little Dixie cups here. Or, I don't know, maybe I guess that's not quite a Dixie cup, but you get the point. And I put some dirt on it, and I put some inside. Okay, so I put some in the house, I put some outside the house. Inside, outside. And so my factors might be temperature, that is inside versus outside, and then also water. And so inside and outside, maybe you have, let's say, 30 of these pods. I'll draw 3 of them because I don't really want to draw 30 of them. And the other side, you have the same amount. Okay? And maybe each of these gets a different water level. Okay? These guys all have temperature in common. These guys all have temperature in common. This might be the low water and the low water. These might be the medium water and the medium water. And the high water and the high water. The idea here being is this. When you let y equal a constant, it's the idea of, okay, let's look at just the outdoor, we'll look at just the outdoor ones. So, in other words, we're going to let temperature remain constant, and we're going to see if there's a difference. Okay, we'll look at the outside ones, and we'll see if there's a difference in water level. And then we'll let the temperature be the inside ones, right? So it's a different temperature, and then we'll look at the differences between the water levels. And then we'll say, well, let's let x equal a constant then. Well, that in this case, this might be the water levels. So let's hold the water levels constant, and let's compare this side to this side. When I compare this side to this side, any change I see in the plant's height, right? Maybe these are all little puny farts because it's cold inside the house. That's weird. Versus these guys, which are nice and big and bulky or whatever. Any differences I see side to side, okay, that's when I was holding the water level the same. Any difference this direction is going to be because of temperature. And so if I compare this plant to this plant, any size difference because of the same water will be because of temperature difference. And that's the whole point of looking at traces nowadays. And that's one of the big reasons. Is because back in the old days you had to try to sketch it. Nowadays I'm interested in, okay, well what kind of a goofy looking thing do I have? And how is z impacted by, let's say, a change in y? Okay? So if you let x be constant, then what I really end up with is some big fat constant plus the cosine of y. Well, that's easy to see. This is y, this is z. A constant plus the cosine. Well, here's with the constant 0, yes? Here's what it looks like if the constant's 2 or something. Here's what it looks like if the constant is -5 or something. But they all have the same general shape in mind. So now if you let y be a constant, what you end up with is 3x squared plus a constant. Well, here's 3x squared plus 0. Here's 3x squared plus 1. Here's 3x squared minus 2, and so on, and so on, and so on. And again, if you look at that in the 3D calc plotter, that one's fairly easy to remedy. Oops, stop it. So 3x, oops, well, wrong calculator, dummy. So 3x squared plus cosine y. Boom. Okay? And again, viewed from the side, there's the parabola that I was looking to see. Yes? That's the parabola that I really wanted to see. And I knew I was going to get a parabola. And you can see there's a skinny one coming down like this, right? And then if you look, there's another one. You can see it printed right on the thing. There they are. If you spin it around and look at it this way, what do you notice? Well, it's cosine and sine business. Yay. Now, could you let z equal a constant here? You could, and it would be weird, but you could do it. So you get a constant is equal to 3x squared plus the cosine of y. Now, good luck with that, because I don't know how to solve for y here very easily, right? I mean, it's doable. You're going to get c minus 3x squared, right? Inverse cosine is equal to y. Okay, well, you know that's just freaking weird looking. Can I graph it in Desmos? You know I can. So it is y. Oh, no, I don't want to stand. Idiot. So I'm going to do arc cosine, arc cosine, there we go, of, and I'm going to go C minus, it doesn't like arc cosine, I guess it's just cosine. Got too many programs, I can't keep track of all of them. Of 3 minus, not 3 minus, C minus 3x squared equals y. Okay? And so we add a slider for C, and it's going to look something like this goofy thing. Okay? So viewed from above, that's what I expect it to look like. So when Z is equal to 10, it's going to look something like that. When I come down and I see Z is equal to 0, it's going to look something like that. And when Z's go negative, it goes down to that. Okay? Interestingly enough, okay, Z can't go too far negative, yeah? Can't go any less than -1, I believe, right? If you look over here, our Z's never go less than -1. And again, viewed from above, okay, viewed from above, they kind of look like that. Now, you could write it another way too. You could come in here and say, well, okay, maybe I want to do it implicitly. Well, good for you. So, cosine of y equals, and then you should be able to do C minus, or C plus 3x squared. Why doesn't it like that? Well, piddle piddle. Could have also written it the other direction as well. You could have looked at it in terms of, you could have done C minus, or Z minus C, not Z minus C. Yeah, try again, Jay. How about C minus the cosine of 3y, cosine of y rather, divided by 3 and then square rooted, right? That should also give you a plus or minus business. Interestingly to note, I don't really need to graph that. Well, I guess I do now because I got rid of the other one. I have to do y equals. In Desmos, it doesn't like it if you try to do it the other way. So square root of C minus cosine of x. I'm going to do it in terms of x. And then I'm going to do this whole side divided by 3. Divided by 3. Oops. Oh, it was the 3 was inside, wasn't it? Yeah, never mind. Let's see. Get rid of that dumb square root. Okay, here, let's try this. And put the square root on the outside. There we go. Oh, crap. Copy. Control X. Control V. Delete. Cool. Add a slider. Bam. And Control C. And Y equals negative. Paste. And so viewed from above, that's a better picture of what I saw than the other one. The other one I must have held my mouth a little crooked. Viewed from above, you see these things, yes? And viewed from above, that is more or less what I see, yes? I see viewed from above, there's little pockets down in the bottom of that thing. Yes, there's little pockets of up pieces and down pieces. And in essence, this is what I'm seeing. If you come up a ways, okay, for instance, you come up on the side of it, there's this little in and out kind of a deal going on here. That's what this is showing me. When I do that, when I say let's let z equal 2.6, that's what I'm saying. When I let z equal 0, we're right down on the axis, and this is what we're seeing in essence. Well, right down on the xy plane, that's what you would see if you chopped it right across there and looked at just a two-dimensional view of it. What you would see are these little little football shaped deals. Alright, so those are the sorts of things you'll be doing in 9.6. You'll be getting used to graphing a few things. Where it says use the traces to sketch the function. No, 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 no. In this section, I do not want you to do that. What I want you to do is I want you to get comfortable using the program, 3D Calc Plotter. I really want you to focus on what's the domain of my function, and I really want you to think about what's the relationship. Is it quadratic? Is it cosine or sine or e to the negative x? What is that relationship? And then sketch out the traces. I do not want you to try to draw them in 3 dimensions. You do not need to, for instance, come in here and, oh, I'm going to copy this picture and paste it into Word or something. I don't need to see it. I feel pretty good with what I see from you. I want you to just practice on it. If you get stuck when it comes to graphing, please give me a call, or an email rather, and I will get back to you and help you out.